Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today on General Physics 1, we want to start to talk about the thermal behavior of matter. That means we are going to discuss matter as well as its behavior if you apply heat towards it. So last time we have talked about the transfer of energy in the form of heat. So now we want to talk about what will happen to the material when you apply those heat. So before we get started, please consider subscribing as well as liking the video if you want more of these kinds of videos. And also, all of the notes will be down in the description below. So let's just jump into the discussion. So the way that we'll actually try to discuss this behavior of matter is by looking through different kinds of matter first. One of them is gas. So last time we have talked about gas, which is a compressible fluid. And so there is a law that you could create from the gas, which you call as the ideal gas law. The ideal gas law. And and this basically states that your gas is a that your gas is a bunch of particles and they obey certain rules that you actually define. So so if you actually try to do this, we would just do this from the perspective of experiments first. After that, we will discuss about the the kinetic theory of the ideal gas. So, if you actually look at an ideal gas and you do experiments towards it, you would you would gain the relation of PV would equal to NKT, or sometimes you could call this as an RT. So, how do you form this formula first? So there are multiple kinds of experiments that were done to try to understand gases. So to try to understand this gas, we will discuss four different laws that was established by looking through experiments. So the first one is what you call as the Avogadro's law. Avogadro's law. So his idea states that the volume must be related to the amount of particles that you have, which you call as small n or big N. Small n in here represents the the bigger mass, which is denoted as moles, while the big N stands for a single particle that you add up add them all together one by one. So this is like only one unit, and this one is like a dozen of those. So that's from the Avogadro's law. The second law is from the Gay-Lussac's law. Gay-Lussac. So he states that the pressure should be related to the temperature. So so if you, for example, increase the temperature 2 times, well, technically it's not really 2 times. No, sorry. It is technically 2 times if you think of it in the Kelvin scale. You would realize that the pressure would also increase by twofold as well. So that's another relation that we discover. The third one is that from the Charles law, it it states that the volume changes with temperature. So if you heat something up by twice the amount, you would get the gas itself to expand twofold as well. And the last one is the Boyle's law. So the Boyle's law tells you that basically the pressure times volume will be a constant. So so it is like the reciprocal of it. And so you could think of this as as the conservation of the internal energy itself, but I will not really discuss fully towards there yet. So with with all of these four laws, you could develop the idea that PV should equal to n times t times a certain constant, which in here it is r, or if it is big N, it is k. So what are the values of these k and r? So first, we should start to discuss about this k here, which you call as the Boltzmann constant, and its value is 1.38 times 10 to the power of negative 23 joules per Kelvin. That's something that you observe. And so this N here stands for moles, right? And N is the amount of particles. So how do you convert from the small n to the big N? Well, it is basically just using just by using a conversion factor, which is the Na, or what you call as the Avogadro's number. Avogadro's number, which is 6.022 times 10 to the power of 23 uh, per mole. So 1 mole contains 6.022 times 10 to the power of 23 particles. And so if you actually convert from this guy to this guy, you would see that the NTR should equal to the NTK as long as the P and the V remains constant. The T would cancel each other out, and you would get R to be the N over N times K, which is the NA times K, which if you actually evaluate the value, this is 8.314 joules per Kelvin mole. So this is the value that we normally use when we do thermodynamics of gas. We use the universal gas constant 8.314 to model the universe. So we have already talked about this experimental fact. And so now I want to discuss a little bit more about the theoretical side and how could you actually obtain these values. So to develop this ideal gas law, you need to set up laws, which is the kinetic theory of ideal gas, of the ideal gas. So what are the assumptions made? First, the gas contains identical molecules, mass m, negligible size. So it might be very small that you don't even need to care about its rotation. You just need to care about its ping-ponging as if it is a point. Second, the second assumption is that the molecules don't have intermolecular potential energy. Molecular potential energy V. No, sorry. I'll call that as U. Only kinetic energy. So this basically states that if you have two particles close together, they won't try to repel each other. They don't even actually attract each other. They might collide with it. They might collide with each other, but all we need to care about is the kinetic energy. The third, the the molecules move in random direction with a distribution of speed. So this basically states that the molecule will move in any direction that it wants, but its speed will be controlled by a probability. And lastly, collisions with Waals are elastic. So basically, this is a conservation of momentum. So this conserve momentum and energy. So with this, let's actually try to derive the ideal gas law, as well as get the understanding of what temperature truly is. So assume that we have a box in which we have a certain volume, a certain pressure, and also it has a certain amount of molecules, which I'll call big N. And oh wait, no, sorry, there's volume and there's also the distribution velocity. So now let's actually think deeply about this. So let's just think of a very small space right over there. So it's basically like a wall there, and there are molecules bumping towards this wall. So you would have the wall, you would have a particle going here with a certain mass m as well as its velocity v. So later, after a certain amount of time, it will later repel itself again. And let's just state a certain length here to be called L. So the question is, what is the what is the time it takes for this molecule to go back towards this original position but a different direction? So you could actually do this by looking at the kinematics itself. So you would know the total length to be 2L, and it moves at a constant velocity. Multiply that by the time. So you would get the time to be 2L over V. So this is the time. And after that, we could ask about the impulse, which should be F times dt. So what's the impulse that is experienced by the molecule will later define what the force is on the wall. So you would know that the change in momentum here is 2mv. It makes sense. And the force, multiply that by the small change of time. So let's just take the L to be very close to 0. So the T would also go close to 0. So this formula could work. And we would obtain the 2L over V. So solving for the force, you would get mv squared over L. So after this, we could now try to develop the understanding of the pressure of the object itself. So the pressure is the force over area. And this would equal to, so by the way, this is only for one particle. So if there are multiple different particles colliding with the walls, it will be basically the sum of each of these mv squared over L divided by the A. And this would equal to, the mass and the length would be constant anyways, so it's m over LA, which is the volume, with the sum of the v squared in one certain direction. So this is something, but I can create something much more interesting for you to actually to look at, which is if I multiply the top and the bottom by n, you would get n over v times m over n, the sum of the v squared x. So here's the thing that you need to notice. This here tells you the average velocity squared, or the root, or the square of the root mean square of the velocity. So you would get n over v. Okay, sorry. Yeah, that multiply that by m v squared x bar. So it's the average of this, and that equals to the pressure. So trying to form this into your ideal gas law, you would get PV, which equals to n mvx squared. So you have defined what the ideal gas law came from, which came from this, and also this part here corresponds to the kT. So that's something interesting for you to think about. The velocity actually corresponds to a temperature. Well, let's dive deeper into this. So we obtain that the mv squared x equals to kT, right? And so if you actually look at the definition of the velocity itself, it will be the root, it will be the sum of the squares of each different component, right? And here's another fact. Every single velocities here would always correspond to the same value for the average. That's something interesting because it has certain symmetry in here. So you could just state this to be the square root of 3 Vx bar squared. So that's interesting for you to look at. So now, oh sorry, that should be a bar. So transforming this, you would get the Vx bar, Vx squared bar would be equal to 3 V squared. No, sorry, V squared over 3. So if you actually transform this again, you would get mv squared over 3 is kT. Well, this is not truly helpful, right? But let's actually multiply both sides by 3 over 2. So we'd get mv squared over 2 and 3 over 2 kT. So here's something that I want to talk about. This 1 over 2 kT corresponds to each different axis that it could move. So if this is a one-dimensional simulation, it it will only be half kT. But if there's 3 dimensions, it is 3 over 2 kT. So it is depending on its degree of freedom. And this relates to its kinetic energy. So that's something interesting for you to think about. You see that the temperature depends on the kinetic energies of these particles. So that's actually the definition of temperature. It is the average kinetic energy associated with random translational motion of molecules. And so with this, we could also determine what is the velocity of each of these particles on average, you could say, which is the v should be square root of 3 kT over m, which is sometimes called as the thermal velocity, VTH. So, you could see here that after certain theories, you could obtain the value of the velocity of a particle within a gas. But after doing much more research, you could actually see that actually the spectrum corresponds to a certain kind of distribution called the Maxwell-Boltzmann distribution. So the value is so this is the probability density. This is 4 pi m over 2 pi kBt, which is the Boltzmann constant, to the power of 3 over 2 v squared e to the power of negative mv squared over 2 kBt. So the value is something like this for a certain kind of temperature. So if you want to study more about this, I I recommend you to try to study thermal physics as well as statistical physics. But I won't really go deeply into this region here. So we have already talked about this formula for the velocity of a ideal gas. So there's something that you don't actually truly discuss much, which is something called the van der Waals force. So what is this van der Waals force? So the simple way for me to say this is that this is the interaction between molecules, which comes from electrostatic and also coming from probability. So I would fully discuss the detail behind how charges attract each other, but this is something for you to consider when taking general physics too, is that you want to try to understand interaction between molecules, which one of these forces is the van der Waals force. So we have already talked about gases, but everything that we actually use right now involves solids as well as liquids. So let's start to discuss about something called the phase change. So you might see phase changes everywhere. For example, ice turns to water, turning to steam, going back to ice, and whatsoever. So I really want to try to understand how this could actually happen. So phase change is basically change in the physical property of material. So the way that you actually try to understand phase change is to actually look at the amount of heat that you apply towards the material, which which you will later gonna try to understand the heat of transformation. So this is basically the amount of energy you need per unit mass to change its phase. So so there are different kinds of these heat of transformation. There is the heat of fusion, heat of vaporization, and the heat of sublimation, each having a different value. And also for fusion, this this basically means that if you have liquid, it goes to solid. For vaporization, from gas it goes to liquid. And for sublimation, oh sorry, it goes both ways. And for sublimation, it's from solid to gas. So the formula for you to determine the amount of heat for you to change the phase of a certain object you call Q is L over M, where the L is the heat of transformation, which is in joules per kilogram. So you would notice here that to change the phase of the material doesn't truly mean that you need to change its temperature. You could state that at 100 degrees Celsius, the material itself could be liquid and a gas together. For example, something like that. But the total amount of heat for you to change the entire thing into vapor is this amount of heat. So that's about the phase change and its heat. So there is a very interesting plot for you to try to understand, which is called the phase diagram. So I will try to discuss a little bit about this. So if you have, for example, the PV here, no, sorry, the P and the T should be here, the P should be here. So if you actually try to plot every single pressure as well as temperature of a material, let's say water, you would get something like this. So this is a plot of the, this is plot of water, H2O, for a certain amount of temperature. So in here, I will state this to be 1 atmosphere. And this is going from 0 to, let's say, oh, sorry. I think I draw this wrong. It should be something like this. It goes like that, and it goes like that. There we go. So this is 1 atmosphere. This is 0. This is 0.01. And, and this one is 100 degrees Celsius. So we have solid, we have liquid, we have gas. So just by looking at this plot, if you could actually keep track of your pressure as well as your temperature, you could determine what the phase of the object is. So this plot could help you to actually try to solve for the amount of heat you need to change from one object to another. And there are certain points that is very important for you to actually to know. So in here to here, it is sublimation, as you know it. There is also from here to here, which you call as the freezing point, and then from here to here, that's boiling. So these points are like the freezing point as well as the boiling points. And there is a point here, which you call as the critical point. This critical point is where the distinction between liquid and gas doesn't truly exist. You could have a liquid that behaves more like a gas, or gas that behaves more like a liquid. So this is where the boundary between liquid and gas disappears. And and so this might be useful for you to actually to understand when you are discussing a little bit about material. And also another one is the triple point. So in here you would have a state which is solid, liquid, and gas. And this is one of the ways for you to tune your thermometer. The way that you tune your thermometer is that you set 273.16 Kelvin to be the triple point of water. That's basically it. And something to notice is that the triple point doesn't truly change. It will always be at that point, no matter in what pressure it is. Compare that to the freezing point and the boiling point, which you could see if you actually increase the pressure, there could be a freezing point which is much more faster compared if you do that within 1 atmosphere. So that's about the phase diagram. So after we have already talked about this phase diagram, I want to talk more about properties of material, which is the thermal expansion. So last time, we have saw that the ideal gas expands when you apply more temperature to it, even though there is certain kinds of boundaries that a gas could have. But this works for liquid as well as solids as well. So the way that I will try to give you the formula for this is to actually to discuss the volume first, after that the linear expansion. So let's do so. So to define the change in the volume, it's basically just the change in temperature, multiply that by a constant, and you would get a ratio here. The change of V over V times delta T. And the unit here is obviously 1 over Kelvin. So with this, you could see that the change in volume is actually much more of a ratio. Compare that with the temperature. So now, let's actually try to talk about the linear expansion. So by the way, this is the coefficient of volume expansion. So if you want to try to transform this into a linear expansion, let's actually think of this as a box with a certain volume, and then we want to determine what the length is. So we know the box itself to be S times S times S. Let's just assume that to be the case. So we could write the change of V over the change of temperature would be beta V. You can just see it from here, right? So this is a differential equation, right? And if you actually plug in V to be equal to S cubed, this would be 3 S squared ds over dt would equal to beta S cubed. So you would get 3 ds, which equals to beta S. So with this, you could see that you would get a delta L, which equals to beta over 3 delta T times the original length, L. So try to rewrite this again. This is delta L over L equals to alpha delta T. So what's this alpha? It's the coefficient of linear expansion. And the value, it is 1/3 of alpha. So that's the way that I will explain this coefficient of linear expansion to be related to the coefficient of volume expansion. And I know that this might seem a little bit not wrong, I would say, but more of a assumption, because in the physical world, nothing is truly the same. But this gives a very good approximation with the correct value for the coefficient of linear expansion related with the volume expansion. So I think that's all for today's video, and I hope that this video is helpful for you all to understand more about thermodynamics and its behavior towards matter. So thank you very much, and don't forget, if you like this video, please consider subscribing as well as liking the video. So thank you very much, and I will see you on the next video. See ya.